Hello, hello? Okay. Sorry I have a low voice, but I'll do my best. Do you have still a little of energy? Last presentation, last quarter of hour? Okay, good. So, proteanTecs is an IP provider and uses the information produced by this IP, this sensing element, for analytics. This is in a nutshell what we are going to see, but this is the, let's say, the technology is not the problem. Power consumption. This is a critical limiter. Starting from the system point of view, I'm not a data center guy, so I'm not going to, let's say, teach you anything about that. But I was told that to scale up data centers, things like the grid, so how much power is needed, this is even a critical factor. This is even considered. Here, what I'm going to do is a deep dive into this power consumption problem, but from the point of view of the silicon device. Actually, there are 3 dimensions, and these are interconnected. Yeah, like the 3-body problem. No, I'm joking. I just binge-watched the series. But, so performance, power, and reliability. They are competing each other. So we have performances that typically they are defined by spec. This is what we want to achieve. At least power is indeed an upper limit, power consumption. And these 2 things must be balanced against, let's say, long-term reliability. So how the system is supposed to live for the entire life. I don't want to bother you with the math, but you know, power consumption ultimately is a function of voltage and frequency. The point is that if we increase frequency, then we need also to, let's say, boost with more voltage, and these ultimately increase the power consumption. So there are very well-known solutions for that. Here, just to mention, we are not going to discuss that. I think that you know by heart these dynamic methodologies like DVFS or AVS. So both are ultimately going to trim down as much as possible these pairs, this V, so frequency or voltage, so to save as much as possible power consumption, but to keep the performances up to what is needed. It is a complex job, so it's time-consuming, energy-consuming, it's costly, and ultimately, because of what can happen in the field, we need to put garbands on top of what could be the minimum voltage required, this VDD. This is just to illustrate what are these garbands, just for the sake of, let's say, demonstration. We're showing here different cases. The worst one, case A, is just showing how temperature, how the workload, so what kind of operation is ongoing, what is the computation that the device is doing. You may have additional things due to the environment. Airdrop is another external factor that could eventually put your device in danger. And this kind of research is done during, characterization, during validation, and with statistical mean, these garbands are defined. Case A is the worst case. Does it happen? Well, I'm an automotive guy, safety manager, so if you ask me, doesn't matter what is the probability, for sure you need to consider it. And so garbands are costly. But in reality, you may have different conditions, right? Aging may not manifest yet, or maybe it's not relevant. Temperatures maybe is not critically high. The workload is using the computational operation is not so demanding, and so on. So ultimately, you have a dynamic situation that changes. So the applied voltage, and this is the goal that applications like AVS, they are trying to do, is actually by the situation, by these factors, they are trying to find what is the actual minimum voltage applied that you need, minimum VDD that you need to apply to keep the system safe, so fully functional, but also but to accommodate these factors, right? And these may change. Now, what we are going to present here is that the state-of-the-art ultimately is a statistical approach, uses indirect measurements to decide what is the best VDD to apply. For example, by knowing the temperature, you may indirectly decide what is your case, right? Just to make an example. What if, indeed, we have an application, we have a direct measure of this impact, and therefore we can decide what is exactly the minimum VDD that we can apply in runtime, so operation by operation. Well, in this case, what I'm going to show you that there is the possibility to use timing margin that is a direct measurement, a direct effect of the applied voltage, the reference voltage. As I said at the very beginning, we're talking about two things. From one side, an IP that is dedicated to these measurements on a hardware sensor, we can say, that measure timing margin, and then an application that uses this information to provide this feedback loop and then to trim down as much as possible VDD. This is just an anticipation. Let's have a look how it works. This is the hardware IP, so a monitoring solution that is connected from flip-flop to flip-flop, and so it's able to measure any logical path that is in between these flip-flops. So we're talking about millions of logical paths. The point is that these agents are small and therefore can be scattered across the digital device under test. And the high coverage provided by them give us the possibility to direct measure what is the timing margin, instead of indirectly measuring it with a kind of canary device, so a logic that mimics what is doing the digital unit. We do not have the time eventually to go through the entire details of the chart, but this is a real example in the sense it's a real project. As you can see here, there are different kind of hundreds of margin agents, and they are actually measuring this timing voltage. I'm trying to use the presentation here. So the minimum timing path is where you are reaching a possible timing violation. So what you do not want to cross, right, for your digital device. And timing margin is sensitive to all the factors that we were counting before when discussing the guard bands. So process grading, aging, what is the actual load, the computational load that the device is doing, so what kind of operation is doing. And so the external conditions, like temperature. A sketchy picture to show you how ultimately it works. So timing margin on the top, voltage below, they are correlated. So let's imagine that you have AVS, so you are adaptive, scaling down voltage. As you scale down voltage, the timing measured by the agents goes down. And so you have ultimately a direct measurement of the impact of this scaling down, okay, of this trimming down. So you can reach a minimum level, it grants you the best combination, so the needed performances, but at no cost of extra power consumption. If anything is happening, like let's say a V-droop, if it's causing the timing margin to further down, drop down, then this can trigger an hardware interrupt, and this is the kind of information that will be fed back to the power management to rise the voltage, okay? This is a screenshot of, let's say, a demo. So on top of an existing silicon device where we are already applying the margin agents to measure the timing. And, well, it's ultimately exactly the same. This closed loop is a dynamic one. So as we see the effect of scaling down voltage, we measure the timing margin, and we control with this hardware firmware loop the power optimization. In this particular project, we have measured something like 11% of power saving on top of existing AVS. So AVS is already working, and on top of the AVS, this further trimming down using margin agent added a further 11% of power reduction. So, in a nutshell, this is the solution that I'm presenting here. So, from one side, we have the input. So, this monitored concurrently with the operation. So, we are in situ, inside the digital unit under testing, in this case, under workload, so is working, not in normal condition. We are monitoring with high coverage the logical path, reporting the worst case, the worst timing margin, and this information then is used by a firmware application to create an input for a feedback loop control in the power management. If, for any reason, the timing margin further drops or suddenly drops below a critical threshold that can be a timing violation, this can trigger a tripwire alert, so an error notification. If you like the word like I do, this can be used as a safety mechanism even, right, for safety purposes or for mission critical purposes. So now, this is a solution, silicon proven. What I encourage here the open community is to discuss eventually requirements or the application for a usage in data centers applications. Okay, then now is time for Q&A. I hope you have still some energy.
Thank you, Andrea. Do we have questions? Of course, I have a question for you. I would like to step back from the technical question, and I would like to ask more a community-focused question. proteanTecs has been active participant of the open community, but also the Future Technology Symposium. You participated last year and also engaged this year. You also have the presentation today, but also the tech demonstration. So what are the benefits for proteanTecs to participate in activities like symposium?
Well, I think that there is I don't want to misuse the word paradigm shift, but the key point of the solution that we are proposing is this concept of monitoring. So instead of detecting, so let's say black and white pass-fail situations, the idea to provide data from within the device then can be leveraged for many different things. And I think that a symposium like this, so an open community, can further think about how to use data, right? So the solution here that I'm presenting you is ultimately a closed loop and quite end-to-end application. But yet, the data itself could be used for many different things. And this is actually where I see a community, how that can step in and eventually leverage this information. So having data, this is always the key factor, right?
And I think you would like to welcome our participants to visit your tech demo?
Yes. Yes, please. There is a dark corner in LA Hall 4 where we do tech demos. There is not only mine, there are also other demos. Over there, actually, I'm going to present a different type of presentation, different type of application. It's about interconnectivity, so die-to-die. But ultimately leverage exactly the same concept. Hardware IP, monitoring, and analytics that uses this information.
Okay, thank you, Andrea.
Welcome.